Hi everybody, this is a quick run through of the ChannelStatsROC function in the NIRS Toolbox. So the ROC curve, or the receiver operator curve, is basically meant to show how often something guesses something correctly versus how often it guesses something incorrectly. In reality, it's the true positive rate versus the false positive rate. So something that has a very high true positive rate versus a very low false positive rate means that you have a very capable or efficient or whatever it is tool. A common use for this in FNIRS would be something like comparing one analysis pipeline to another. So let's say you wanted to see if adding PCA to your pipeline improves your statistical tests. So not necessarily that you get more statistical significance, but you get more correct statistical significance. So what you would do is basically run your pipeline with PCA, run your pipeline without PCA, and you'd plot an ROC curve for both, and then you would compare those two. You can compare them either visually, or you can compare them using something called area under the curve, which is basically the area under the curve and gives you a single number that you can compare against each other. In order to do this, in order to actually compare two things, you actually need a data set that you know where the items of interest are. So that when you guess them correct, you know that you guessed them correct. And when you guess them incorrectly, you know that you guessed them incorrectly. So in this function, there are three properties that you can call, that you can load into it. One is simfunc, which stands for simulation function. That's how you simulate data. There's two ways to do that, and there's a few varieties within those two ways. Artfunc, which I'm actually not sure what it does. I haven't seen any examples of that just yet. I haven't dug into it enough. But you can run the function without that, so I don't think it's of too much focus at this point. And then pipeline. Pipeline is basically how you want to run the data. So whether or not you use PCA would be an example of that. And then finally, when you do run this, or when you do prepare this job, or this function, you can actually run it just like you would a normal job in a pipeline, and you can draw it. So to do that, you would save it as a variable. You'd say variable.run, and it would run this job. And if you wanted to see the outcome, you'd say variable.draw to see the outcome. So the simulated data can be called either doing sim data or sim data set. There are a few aspects that you load into the data set, or to this function. One is noise, that's the data itself. One is stim, which is various stimuli that you're going to add in. Beta, which is going to be a weighting coefficient. Channels, which are the channels that you want to apply activity to. I'll say activity to. And then basis, which is actually within this is going to run a GLM, and you need a basis function. By default, that's a canonical href. It's just a little bump like that. So if you load in data, which would be the noise, the output would be your initial data mixed in with various stimuli. And at each stimuli, you would increase a nice bump in the data. You'd add to those points. If you don't add in data, you just leave it blank with a little square bracket box, you will simulate autoregressive noise. And so it'll just be autoregressive noise. And again, you'll add these random bumps at set stimuli. If you import stimuli, that's where you will add the bumps. If you don't, it will auto-populate random stimuli. The beta is how big of a bump you're going to input. And by default, I think the toolbox uses 7, although you can change that. I don't know of a reason you would need to. If you increase the bump, I would imagine that your guesses on your ROC would be better. But you'd probably want it appropriate for what you expect your actual task to impact the brain activity with. Channels are the channels that you want to modulate. So which channels you're going to add a bump to. You don't want to add it to all of them, because then you'll guess incorrectly more often. It'll be too easy to guess, let me put it that way. And then basis function, you can actually leave blank. It's probably okay to not change that. However, you could change it to a different basis function if you prefer. So if you put in the data, it's a little screwy. because if you load in your own data, you have other stimuli built in that you're going to kind of ignore. And it's probably not ideal in my mind that you would do that. I like the idea of doing autoregressive noise and then throwing in activity on top of that, because it's a little less biased in my mind. However, perhaps adding data in is more correct, because you'd have kind of simulated brain activity that's not, that would be more likely as in an experiment. If your subject's facing a screen doing some various tasks, the brain would be wandering and doing other things. If you don't put in noise or any data in, it will do what's a function called sim AR noise, and it's just going to give you autoregressive noise. And it's very simple and clean cut, in my opinion. What this looks like, if I load in a data set, this is my data set on the left, what I get as output after running it through sim data is shown on the right. As you can see, the data looks almost identical, just different color, but I have a whole lot more stimuli. Those are these little bumps down here on the x-axis, essentially. However, this data is not identical. It's almost identical. They've added in extra bumps that you can't quite see simply at those locations. So now you actually have a little bit more variety in the data based on that at set channels. If the differences are shown here, so basically comparing the left data set to the right data set, this is what you get. All these vertical lines on the right in blue show each data point that is not the same. So you can see most of the data is not the same. It may not be vastly different, but it's not the same number. On the left is actually the difference between the two. So you can see over time, you actually do have modulations. They're very small. It's to the 10 to the negative 3 power, but they modulate at a set pattern almost. And this pattern is basically those basis functions added on to the stimulus. So that's what you see there. If you load in the sim function with no data, no stimuli, and no channels, it's going to auto-populate this. And what you're going to get is fully simulated data. And this is autoregressive noise here. These are random functions, random stimuli thrown in. And what I've found is when you do this, if you don't also list normally you're loading in a full data set, you have a montage and all that. This is fully random. So it actually seems to always locate 9 sources and 8 detectors and always 32 channels. I've done it maybe 5 times, and each time it's the same. So I imagine it's the same throughout. This is a basic pipeline for what you'd want to call. You create the sim function, call it with a whole bunch of blanks. This is the beta coefficient, so it's just how big of a bump it is. And I stole the default, so I don't have a reason for using 7. You create the job. NIRS, in the NIRS folder, in the testing subfolder, there's a ChannelStatsROC function, and it's empty. It has a variable or a property in it called simfunc, and I call it right there. So I'm going to load that in, and then I'm going to run it. This number here represents how many iterations I'm going to run this on. So I'm going to test it several times and see how often I get these responses. To keep in mind is if I have a 20-channel montage and I run 10 iterations, normally you would have, let's say 20 channels, 1 condition. Normally you'd have 20 t-statistics, right, with 20 p-values. But I have 10 iterations. So at that point, once I do 10 iterations, I have 200 t-statistics and p-value, associated p-values. So your data will change a little bit based on that. Not the data, but this output will. So as I've kind of gone through, the simulated data just shows either completely random data, or it shows an autoregressive data with embedded bumps for activity along various stimuli, or it shows your actual data with those bumps added in. It's going to use this truth vector, which is just the list of channels that you added the bumps to, as the actual comparison factor. So how accurate were you? This is going to compare to this truth vector. If you don't include a pipeline into this sim function, or excuse me, into this ChannelStatsROC, if you don't include a pipeline, by default, it will perform this: resample, optical density, Beer-Lambert law, and then a GLM. The GLM will actually do the F test against rest and will give you your statistical values and will enable the ROC curve. However, there's a good chance that the reason you're running this is because you want to compare pipelines. So you don't necessarily want this default. So in a moment, I'm going to show you how to vary the pipeline, but we'll move into something a little different. So the example, I think number 2 in the function call is where it shows how you can actually convert the pipeline and embed something a little bit different. So here you have basically the same pipeline, but of course you can change it how you wish. You resample, you go to optical density, you do Beer-Lambert law, you perform the autoregressive IRLS, and ignore the verbose thing. It has to do with the little grid showing you how much is done. And then you do a mixed effects model here. So now everything's saved in this P variable. I'm going to call the ROC function, and here I'm going to input the pipeline. Then I'm going to create a simulated data set. And this, again, you have to use this @ symbol here because you're embedding a function as an input to a function. So it's kind of a version of that function. And it's going to use some default values in that, one of which is going to use AR noise. So it's going to develop AR noise on that. And then your output that you're going to get, again, you're going to do, here you're going to have test. To run it, you do test.run with parentheses attached. And then to draw it, you do test.draw with parentheses around it. The output is going to be 2 plots. One looks like this, one looks like this. This is the actual ROC curve. So basically what you're saying is you have HBO in blue, HBR in red, and then the joint combination of the two. If you draw a perfect diagonal here, that would be random chance. What that shows you is if I just guessed how often would I be correct and incorrect, it would be this diagonal. Anything above that diagonal is better. Anything below that diagonal is worse. Ideally, anything you do would be above. And ideally, anything you do that's good will be quite a bit above. What you're basically saying is that HBO used alone dictates activity well, but not that well. It's a little bit better than chance. HBR by itself does actually a little bit better than HBO in this case. But if I combine the two, they actually do much better. And a perfect job would be where this line goes perfectly up to 1 and then just does a right degree turn and over, or very, very close to that and over. A very, very poor one would be flipped on that, and it would go all the way to the right and then go up. To compare these, you can visually look at them as we did, but you can also do what's called area under the curve. And I'm sure there's a MATLAB function for that. I haven't dug into that yet. But you could simply say, what's the area under the curve? You get a value out of that, and the bigger the value, the better performance you have. The next output is this, and actually just to point out, this is the graph itself is comparing true positive rate on the y-axis, false positive rate on the x. On the true positive rate, that's how often you guessed it was active, and it actually was. On the false positive rate, it's how often you guessed it active, and it was not. The second graph that prints out is the estimated p-value on the x-axis and the actual, so the false positive rate, which is the p-value, and then the actual false positive rate that you got on the y. So what I think this is showing, this is fairly new to me, but what I think it is showing is basically you get a p-value attached to every statistic that you run, and you can actually do a permutation. I think I wrote permeation test. Ignore that. It's permutation test. So you can do a permutation test, which is just mixing up values randomly and seeing how often you actually get comparable results, and that's by chance. So we have a p-value attached, and then we actually do this permutation test, and we test to see how often we get that. And what you would expect is something along this diagonal here, but what we get is something that veers from that. I don't quite understand why, let me rephrase that. I don't quite understand what this is showing. So if it veers drastically, I would just assume that the p-value maybe is not so reliable, or that maybe you need more tests or something like that. I'm not certain on that. But that's the second graph that prints out. The graph of interest, though, for most people is going to be this ROC curve. I hope this was helpful, and I hope this gives you all the insight you need to both understand what this is doing and also helps you actually implement it in the NIRS Toolbox. Again, the main aspect that I can see the use for this would be comparing pipelines. It's not necessarily perfect. You're simulating data. You're doing your best with that, but it's a very good way to kind of dictate what kind of pipeline you might want to use in various aspects. Anyway, I do hope this was helpful, and I'll be putting up videos as often as I can. Thank you.